page 104, section 2.5 is continuity. Continuity. When we give a definition of continuity, we've been saying that if a function is well behaved, that we can also call that continuous. And so there on the top of 104, it says we noticed in section 2.3 that the limit of a function as x approaches a can often be found simply by calculating the value of the function at a, simply by doing direct substitution. Functions with this property we've been calling well behaved. They're also called continuous. And so if we want to give a definition for continuity of a function, they tell me that a function f is continuous at a number a if the following is true. The limit of f of a as x approaches a will be equal to f of a. So in essence, they're saying that you can use direct substitution and it'll be well behaved. There's a practical way that we can test for continuity, and that is our informal test or practical test for continuity is going to be, can you draw the graph of the function without picking up your pencil from the paper? Anywhere you have to pick up your pencil when you're drawing your graph, you have a discontinuity. So for instance, if I were looking at example number 1 down here and they asked me to tell where do you have discontinuities, I would go through and I would say, okay, I'm fine until I get to 1. And when I get to 1, I have a hole in my graph. So I'd have to pick up my pencil, jump over that hole, put it back down to continue going. So I have a discontinuity at 1. Then I'd keep going and I'd get over here to 3, and at 3 I have to pick up my pencil and come all the way up here to continue drawing my graph. So I would say I have a discontinuity at 3. And then I continue on from there and I get to 5 and I have to pick up my graph to come up here and put a dot and skip over the value at 5 and continue on. So if I'm using that informal test, I would say that I have a discontinuity. For example 1, I have a discontinuity at 1, at 3, and at 5. I need to know why it's discontinuous. Most of the time they're going to ask me to justify why I'm saying my function is not continuous, to justify the discontinuity. And so these are the, this is the formal test for discontinuity. It's a 3-part test. And these are the only things that I can also use for justifying that a function is continuous or for justification of stating a particular place that it's not continuous. So here's our 3-part test. We said the definition of continuity was that the limit had to equal f of a. Well, if the limit has to equal f of a, both of those things would have to exist. They'd have to be defined, right? So that's parts 1 and 2, that f of a has to actually be defined and the limit at a actually has to exist for me to then turn around in part 3 and be able to say that they're equal to each other. So for my test, I'm going to go through and I'm going to check and make sure the function is defined at a. I'm going to check and make sure the limit exists at a, and then I'm going to make sure that the answers that I just got to part 1 and part 2 are equal to each other. So if we come back to example number 1, they ask me not only to tell where it's discontinuous, but to also tell why. So again, I only have these 3 things that I can give as to why my function is discontinuous. So we already found out there was a discontinuity at 1. I had to pick up my pencil there when I was drawing my graph. So I go back up to my 3-part definition and I say, okay, first off, is my function defined at 1? Well, no, there's a hole in my graph right at that point. So that's my reason then. My function is not defined at 1. F of 1 is not defined. There's a hole in the graph there. When x is equal to 1, y equals nothing. So that would be my justification for my discontinuity. All right, the second place that we said that this was discontinuous, that I had to pick up my pencil when I was drawing it, was at 3. So again, for my justification, I have to go back to these 3 items. So I can say, is f of 3 defined? Well, yeah, right down here, we can see that when x is equal to 3, y is defined. Looks kind of like maybe -1 or -2. They didn't give me a y scale here. But yeah, that function is defined. All right, so then I look at number 2. Does the limit exist? Well, if I look at the limit approaching 3 from the left-hand side, it's down here at like that -2. But if I look at the limit as I approach 3 from the right-hand side, it's up here at like whatever that is, +3 or 4, something like that. Both pieces of that graph are not converging on the same value, right? So the limit from the left definitely does not equal the limit from the right. So therefore I would say that limit doesn't exist at 3. So it's the second part of my test that failed that time. The limit from the left did not equal the limit from the right. All right, so then I look at the last place where I had a problem, and that was over here at 5. And so I know that I have a discontinuity at 5 because I had to pick up my pencil when I was drawing my graph, but again, I need a reason. So I come up here and I say, okay, is f of a defined? Well, yeah, right there. When x is equal to 5, y is equal to that value up there, whatever that is, maybe positive 5 or something like that. Number 2, does the limit exist as I approach 5? So I can look at this and say, okay, as I approach 5 from the left-hand side and from the right-hand side, both of those are converging on the same value, right? Both pieces of the graph from the left and from the right are converging on that same y value, so yes, the limit exists. My problem for this one is the third part, because my limit exists down here at like positive 1, but f of a is up here at like positive 5. The limit doesn't equal f of a. So that is a fantastic example because they go through and show us how, okay, I can look at a graph and intuitively know where I have discontinuities because it's where I pick up my pencil, but what's the reason for that? And so we got an example of what each part of that formal test would look like when it failed. So the first one at x equals 1 shows us how the first part of the definition or the test could fail. X equals 3 shows us how the second part of the test would fail, and x equals 5 shows us how the third part of the test would fail. All right, what if I don't have a graph? Because we know so many times we don't have a graphing calculator. We have to do this algebraically. And so that's the case in example number 2. In example number 2, they just give me equations, and they ask me to determine where they're continuous and not continuous. So let's assume that I don't have access to my graphing calculator. I'm on a part of the AP exam where I don't have a calculator and I'm asked to give continuity. I'm going to look at this first function right here, and we already have a rule for rational functions and where they're well behaved, right? And since well behaved and continuity are the same idea, we could apply that where we could go through and we could say rational functions, their limit exists within their domain, right? So what's going to be excluded from the domain here? What? 2, right. This thing is going to have 0 in the denominator at 2. If I went through my 3-part definition to try and give a reason for why there's a problem here, the very first one right here, f of a is defined. My function is not defined at 2, right? So I can say, okay, I know I'm going to have a discontinuity at 2 because f of 2 is not defined. I might have a discontinuity somewhere else as well. So I need to keep going with this and say, okay, where does my limit exist? Now, if we know that limit law, that the limit of a rational function is the limit exists or the limit is well behaved within its domain, then I could say, okay, 2 is the only value excluded from this domain, so I know it's going to be okay. Or I could use that algebraic method that we were using earlier in this chapter where we would go through and say, is there a way to simplify this down? And sure enough, when I simplify it down, I have a polynomial. And I know that polynomials are well behaved. So I know that I'm not going to have any trouble finding my limit at any other value except for at 2. So the only place that I have a problem here then is 2. All right, look at the next one. For the next one, we've got a piecewise defined function. Where do we typically have trouble with a piecewise defined? If there's going to be a problem with a piecewise. Yeah, they're not well behaved where the two pieces come together, right? So I always want to check a piecewise at whatever the value is over here where those two pieces are coming together. I always need to check there. So that goes without saying. Before I ever begin a piecewise define, I'm always going to check where the pieces come together. But let's see if there's anywhere else that I would need to check besides 0. All right? If I go through and I start with f of a is defined, then I could go through and say, is there anywhere that this function would not be defined? 0 in the denominator, negative under a square root. Well, I run the risk of a 0 in the denominator right here. That's when x is equal to 0, right? But you'll notice that they have redefined that function there. When x is not equal to 0 is when I'm supposed to use this guy. When x is equal to 0, it's defined elsewhere. So yeah, the function is defined. F of a is defined at all values, including 0, where this guy is not defined. So I'm okay there. So then I need to think about the limit. So I can think about, is there anywhere that this limit wouldn't exist? Well, this is a rational function. And again, we know that for rational functions, their limit exists within their domain. So for that guy, I may still have a problem with its limit, even though I've gone and redefined it at 0. I don't care about what's going on at the point. I care about what's going on as I approach that from the left and from the right. So I do still need to check that limit. And so sure enough, when I'm looking at 1 over x squared and I'm looking at it from the left and from the right, numerator is staying the same, denominator is getting smaller and smaller and smaller, overall fraction does what? Gets bigger and bigger and bigger, right? So if I take the limit as I approach 0 from the right or 0 from the left of that thing, it goes to infinity. That limit does not exist. So I can stop right there and say, okay, I know that I'm going to have a problem at 0. The limit as I approach 0, either from the left or from the right for that function, does not exist. So then there's no need to even check that third part, because we already said we would need to check it at 0, but I've already proven that it's discontinuous at 0. So, you know, if the limit doesn't exist, the limit surely isn't going to be equal to f of a. I don't have to give two different reasons for that. One is sufficient. All right, so look at the last piece. For the last piece, we have this same function that we had back here for when x is not equal to 2, and then we have 1 when x is equal to 2. All right, so when I first look at that and I'm thinking about my test, first off, is f of a defined? Is there anywhere that this is not going to be defined? Well, yeah, I would get 0 in the denominator when x is equal to 2, but they have redefined x equals 2 as a different value. So is there anywhere that this function is not defined? No, it's defined everywhere. So I'm good with the first part. With the second part, I need to figure out, does the limit exist? Well, we said that a limit is going to exist for all values within the domain of a rational function. 2 is not in the domain. So I need to be careful because the limit may not exist at 2. I'm going to have to go check that. I'm going to have to go check the limit from the left and from the right. So if I think about that limit as I approach 2 from the left and from the right, I could factor and cancel, and what I'm left with is a polynomial that I could do direct substitution, and yeah, that limit does exist. So the function is defined at every value, because the only place we had a problem was at 2, and it was redefined down here. The limit does exist because this is a polynomial and this is a rational function, and for my rational function I checked it and the limit did exist. So now the third thing that I have to check is I need to make sure that the limit is equal to f of a. How do I know where to look for that? Like I'm supposed to check those things are equal, but how do I know what a value to use? Well, remember we said with a piecewise, the problem occurs, if it's going to, where the pieces come together. So I want to check this at 2 because that's where my pieces came together. So if we check this at 2, if I think about, is the limit at 2 the same thing as f of 2? Well, the limit at 2 we just showed was 3, and f of 2 when x is equal to 2, the y value is defined as 1. So f of 2 would be 1, the limit would be 3. So since the limit doesn't equal f of a, then that would be my reason for discontinuity. So again, another fantastic example where they've gone through and showed us every part of that formal test for continuity. They showed me how every part of it could fail in an equation setting. All right, so on page 105, they give me some bold print terms. They talk about a removable discontinuity. And they say the kind of discontinuity illustrated in parts A and C that we just looked at is called a removable discontinuity because we could remove the discontinuity if we just redefined the function at one single value. So back here, if we had defined this function at one value, at 2, it wouldn't have been discontinuous. I wouldn't have had a hole there. And the same story over here. The only place that there's a problem is at 2 because f of a doesn't equal the limit at that one value, but everywhere else is fine. So in each of those cases, if I redefined my function at just one point, it would be continuous. That's called a removable discontinuity. The next bold print term they give me there is an infinite discontinuity. And that's what we had here in this second part, because remember when we took the limit from the left and from the right, it went to infinity. So if you get an infinite limit that causes a discontinuity, then we call that an infinite discontinuity. And then the last one, D, is called a jump discontinuity. And that's just because the function jumps from one value to another. So a good example of that would be like our step function. The most common example, the one that we've looked at most recently, was the greatest integer function, where from the left and from the right at the integers, we get different values, and so we have those stair steps, we have those jumps. So that means that I would have a jump discontinuity at each integer, at 1, at 2, at 3, at 4. Remember that for the greatest integer function, the limit existed everywhere except for at the integers. So for example number 3, over on page 106, they talk to me about, okay, maybe your function isn't continuous for all real numbers, but sometimes your function might be continuous from the left or from the right. What do they mean by that? Well, on 106, it says a function is continuous from the right at a number a if the limit as you approach a from the right is equal to f of a. So maybe the limit from the left and the limit from the right are not converging on the same value, but if the limit from the right is the same thing as f of a, it's continuous from the right. Similarly, continuity from the left is if the limit from the left is equal to f of a. So if we go back to our step function down here, our greatest integer function, and we say, what's the limit as x approaches 2 from the right? Well, that's like 2.1, 2.01, 2.001. All those values go back to 2 because that's the largest integer that's less than or equal to those numbers. Whereas if I approach 2 from the left, all of those, like 1.9, 1.99, 1.999, they all go back to 1, right? Because that's the largest integer that's less than or equal to that number. So overall, the limit at 2 doesn't exist, so this can't be continuous at 2. But if I do f of 2, that means, you know, when I put 2 in for x, what do I get for y? Well, if I do greatest integer function for 2, the whole number that's less than or equal to 2 is 2. So even though this function is not continuous at 2, if you'll notice, the limit as x approaches 2 from the right and the f of 2 are the same. So they told me on page 106 that that would be continuous from the right because the limit from the right is equal to f of a, it's continuous from the right. If the limit from the left had been equal to f of a, we would have said it was continuous from the left. So it is possible for a function to be continuous from one side only. All right, so here is our homework for tonight on pages 112 to 113. Please note that on number 3, in the back of the book, they're going to use answers like jump discontinuity and infinite discontinuity and removable discontinuity. We can't do that. For AP, when they ask me to justify a discontinuity, I only get to use these 3 things. So I don't care what the back of the book says. When you justify, you only use one of those 3 things on number 3.